today we're going to take everything we've learned so far in this chapter and put it all together and solve for global maxima or global minima. And like I said before, a global maximum is just the overall maximum, you know, on the entire, either the entire function or it may be just an interval of the function. And then of course the global minimum is the overall minimum. It's the least, the smallest point on the function. So we have a couple of different kinds of, a couple of different situations where we may need to find global maxima or minima. One of those situations is just if we have a closed interval where the function is only defined between 2 points, okay? And then, you know, like it's showing here in the diagram, you have to check your critical points where the local maxima and minima occur. But you also have to check the endpoints, because you can have a global, I'm going to use my mouse here. You can have a global maximum or a global minimum at one of the endpoints. It doesn't have to be just at one of the local minimums or maximums. Okay, so for example, in this figure here on the left, you can see that we have one of the local minima is actually the global minimum, right? But the local maximum, there's one local maximum here, well, and I guess sort of over here too, but the endpoint is actually where the global maximum occurs. Okay, so that's one situation where we have a bounded interval for the function, and if we don't have a bounded interval, then we're going to just look at the local maximum and minimum. But we also have to look at the overall function, because in this example, you know, here's a global minimum down here at this point, but there is no global maximum, because on either side here of the interval, you know, this function just goes on, you know, to infinity, right? So there is no maximum. Okay. And we can also get a case where there's no maximum or minimum. If we have a function that looks like, let me just sketch it over here, you know, we have something that looks like that, right? We have local maxima and minima, but there's no global maxima or minima, okay? If it's not restricted to a certain interval. Okay, so that gives you a couple of different situations. We're going to look at the same function that we've been looking at for the whole, in the last two sections. It's the same function, x cubed minus 9x squared minus 48x plus 52. Okay, and we've already kind of analyzed this in both 10.1 and 10.2, but we're going to look at it again to find global maxima and minimum on this function. For this closed interval. Okay, so now we've got a closed interval, and so we're only concerned with this function between -5 and positive 14, where x is between -5 and positive 14. So let's take a look at this function. Now we've already done a lot of this, but it's easy enough. It's a polynomial, so it's easy enough to look at the first derivative, right? It's 3x squared minus 18 18x minus 48, right? And we did this before, but let's do it again. Factor a 3 out. X squared minus 6x minus 16, okay? And I'm doing this because I want to factor it, so I get 3 times x minus 8 and x plus 2. Okay, we want to find if we want to find the critical points, we set it equal to 0. So we have critical points at x equals minus 2 and positive 8. Okay, so if we want to know now, because it's a polynomial, the easiest way to tell whether these are local maxima or minima is to take the second derivative, because second derivatives are really easy with polynomials. So I'm just going to take the first derivative and take the derivative of the first derivative, and I get 6x minus 18. Okay, and now if I look at the concavity at those two critical points that I found, so I'm going to look at minus 2, I plug that in, I get minus 12 minus 18, so I get minus 30, which is less than 0. So it's concave down. Right? And if I look at the concavity at the other critical point, I get 48 minus 18, which is positive 30, greater than 0, so it's concave up. Okay, so now we know, which we already found, before, we know that there's a local maximum at x equals minus 2 and a local minimum at x equals 8. Okay? Now, so we've got our local maximum and minimum, but now in order to evaluate the function and find its global maximum and global minimum, we have to evaluate the function at not just these local max and mins, but we also have to look at the endpoints. So let's do that next. Let's just take the two endpoints, so we have an endpoint at minus 5 and at 14, and evaluate the function at those 2 points plus the maximum and minimum, and then we'll just pick the biggest and the smallest ones. All right, so that's all we're going to do here, is we're going to just, let's plug in minus 5. If I do that, I don't know if I want to write all this out every time. I plugged it into my calculator. It's probably easier than writing out this equation. I'll write it out for the first one. But, oops, okay. Minus 5 plus 52, okay. So I put that in my calculator and I got a minus 58, okay. If I evaluate, let's just evaluate them in order. So f of minus 2, and we already know this from previous lectures, that the value at minus 2 is 104. The value of the function at 8 is minus 396, and if I evaluate the function at 14, I get 360. Okay, so that means, okay, we're looking for the global maximum. Right, I'll just write global max. And the global max, I just look at all these values and it's like, okay, there we go. That's the biggest one. So the global max is 360 at x equals 14. Okay. And the global minimum is, look at all these and I say, okay, this is the smallest one, minus 396 at x equals 8. Okay, so I have now determined my global maximum and global minimum. And that's all there is to it. So let's look at some more practical problems. We're given some kind of practical situation to apply this to. All right, so let's look at example 2. Here, let's see, it says for time t greater than 0 in days, the rate at which photosynthesis takes place in the leaf of a plant is represented by the rate at which the oxygen is produced. And we're given an equation for the rate at which oxygen is produced. Now, it always bugs me when they don't put units on here. It's like, okay, I'm gonna say this is milliliters per day. Let's say that this leaf produces, if we put in a particular T value and evaluate it, that's going to give us milliliters per day. We'll just say that. Milliliters of oxygen. And we want to know when is the photosynthesis occurring the fastest and at what rate. So I suppose maybe when the leaf is growing, it's at first when it's in that growth phase, that maybe it's producing more oxygen because it's using carbon dioxide in the air to I don't know, if it's considered metabolizing that carbon dioxide, but it's using carbon dioxide, right? And so it's expelling oxygen. So maybe during its growth phase, it produces more and then eventually levels off. I don't know. That's what we're going to find out. We'll have to evaluate what this function looks like. All right, so I'm going to take the first derivative. I want to find the maximum, right? So the first thing I need to do is just find the local max and mins. So if I take the derivative of this function, I get 100, and then I'm just going to take the derivative of the inside, and I'm going to get minus 0.02 e to the minus 0.02t. Okay, so I'm just using the chain rule on e to the x, where x is minus 0.02t. Okay, and if I take the derivative of this other term, that's minus 0.1 comes down to the front, so it's going to make it positive 0.1 e to the minus 0.1t. Okay, so that's the derivative. We need to set it equal to 0 to find our critical points. So first thing I'm going to do is just divide both sides by 0 or by 100, and then I'll just get I'll get this thing in parentheses equal to 0. And so that means that 0.1 e to the minus 0.1t is equal to, and I'm just going to add 0.02 e to the minus 0.02t to both sides. So this becomes 0.02 e to the minus 0.02t. Okay. And now I'm going to divide both sides by this 0.02. And I end up with 5 e to the minus 0.1t is equal to e to the minus 0.02t. All right, so this is where we have to remember how to solve exponential equations. So I'm going to take the logarithm of both sides. Okay, and when I take the logarithm of a product, I can turn it into a sum. So I'm going to get the natural log of 5 plus natural log of e to the minus 0.1t, which just becomes negative. So I should probably just make this minus. So I'm just going to end up with minus 0.1t. And I take the natural log of the other side, and I'm going to get minus 0.02t. Okay, and then I can add 0.1t to both sides. I get the natural log of 5 is equal to 0.08t, and so t is equal to the natural log of 5 over 0.08. If I put that into my calculator, I get 20.12 days. Okay, so we have a critical point. This is our critical point. Critical point. Okay. Now we have to decide, is that a maximum or a minimum? So let's look at the second derivative here. This is not too bad to look at the second derivative. Okay, what's the second derivative? I got the first derivative up here. So I am just going to do it again. Take the derivative of this, and I get, now it becomes a positive 0.004 e to the minus 0.02t. And then I take the derivative of the second term. I get, okay, I'm going to bring down the 0.1. So I get minus 0.01 e to the minus 0.1t. Okay. Now, if I evaluate my critical point, okay, now I'm just going to put this in my calculator. I'm not going to write it all out for you. When I put it in my calculator, I got a negative 0.107, which means that it's concave down. Concave down. So when it's concave down, right, it's concave down, that means there's a local maximum at t equals 20.12 days. Okay, so we have a local maximum. Now we really don't have, we've got t is greater than or equal to 0. So the only endpoint we have is 0. So if we evaluate the endpoints, evaluate the endpoints and the extrema and the local extrema. Okay, so if I put in 0, t equals 0, I get 100, and then when e to the 0 is just 1, actually I have to go back up to the original equation, right? So I just get 1 minus 1, so 1 minus 1, it's just 0. Okay, so t equals 0, there's no oxygen. The rate of oxygen production is 0. Okay, so let's evaluate the local maximum that we found, and that's, let's see, 20.12, when t is equal to 20.12, I put that in my calculator and I got 53.5. And like I said, I'm going to assume that that is milliliters of O2 per day. Okay. All right, so, and it's concave down, right? So, and there's only one critical point, so it's not going to get any bigger than that. So the conclusion is that we have a global maximum of 53.5 milliliters of O2 per day, right, at t equals 20.12 days. Okay, so that is our conclusion. All right, so let's look at another example. Let's keep going with these examples. All right, so for this one, we've got a flat sheet of cardboard, 16 by 20, and we're going to cut squares from the corners and then fold up the sides to form an open top box. Okay, and in order to create a box with maximum volume, what size squares should be cut from the corners? And what is the maximum volume? Okay, so let's draw a picture of what this looks like. So I'm just going to draw a rectangle over here, so that I can picture what this looks like. Trying to draw a decent rectangle. Okay, and then we're going to cut squares out of the corners. So pretend these are squares that we're cutting out of the corners. Okay. And then we are going to then fold it along these lines, these dotted lines that I'm drawing. Right, we're just going to fold up those sides and form an open top box. Okay, and we're given that it's 16 by 20, so it's 20 inches in this dimension, right? And it's 16 in this dimension. Okay, now we don't know what size of these squares are, but we do know they have to be squares. And so I'm just going to assume this is, each one of these is just an x by x square. All right, and that's kind of our variable. That's what we want to find out. What size of the squares do we need to cut out? All right, and we're trying to maximize the volume of the box. So we need an some sort of an equation for the volume of the box. And the volume of the box is just going to be length times width times height. And when we fold up these sides, the height is just this x value. Okay, so we need to lengthen the width. Now, the width is 16, so the width of the final box is going to be 16 minus 2x, right? This width here, which will be the width of the final box. 16 minus 2x. Okay, and if we, let me see if I can write sideways here. We need the length here, right? And so if we're starting out at 20 and then we're cutting out two pieces of size x, so this is going to be 20 minus 2x. Okay, that's going to be the length of the box, the final box. Okay, and then of course the height is just going to be x. So the volume, I'm going to write an expression for volume in terms of x. All right, we have 16 minus 2x times 20 minus 2x times x. So that's oftentimes the hard part. It's just figuring out what your equation is. And on a lot of these, it helps to draw a picture. So now we want to maximize this. So what we want to do is take the derivative and find the critical points. But first of all, I'm gonna simplify this a bit because I would rather make this into a polynomial and take the derivative of that rather than trying to use the product rule, and it gets kind of ugly. So what I'm going to do is I'm going to multiply these two binomial terms or binomial factors together. So I'll get 320 when I take 16 times 20. Negative 2x times 20 gives me minus 40x. And then 16 times negative 2, that gives me minus 32x. And then I'm going to have plus 4x squared. Okay, and then that's still times x. And now what I think I'll do is I'm going to rearrange this because I usually like my polynomials in descending power order. So I'm going to end up with 4x squared. I can combine these two middle terms and get, let's 72x plus 320, and then let's just multiply through by x. So, oops, multiply through by x. So I'm going to get 4x cubed minus 72x squared plus 320x. Okay, so now I've got my volume in a nice polynomial form so that it's really easy then to take the derivative of it. Okay, so use the power rule. We're going to get 12x squared minus 144x plus 320, right? All right, now I want to set this equal to 0, which means I want to factor it. So the first thing I'm going to do, because I want to work with smaller numbers, is factor out a 4. So I get 3x squared minus 36x and plus 80. All right. Now, I want to set this equal to 0. I would like to factor this, but this does not factor nicely, which is the way things usually go in the real world. You don't get nice polynomials that factor nicely. So I'm going to use the quadratic formula. Okay, so remember negative b plus or minus the square root of b squared minus 4ac all over 2a, right? So, all right, so negative b, that's 36, plus or minus the square root of, we have to take 36 squared minus 4 times a times c, all over 2a. Okay, the a is this 3, so it was all over 6. All right, now this is where I'm going to use my calculator, because, yeah, this doesn't work out nicely. But the two answers that I get, when I do the plus version, I get 9.055, and the minus version gives me 2.945. All right. Now, this is where we have to kind of use our, we have to go back and make sense out of this. Now, this box is only 16 inches wide. So if I try to cut corners out of it that are 9 inches wide, that is not going to work. So this is not a solution. There's no way that could be a solution. This is the only possible solution, where it's about 2.945 are the size of the squares that we're cutting out. Okay, now I could have put bounds on this one. Essentially the values for x have to be somewhere between 0 and 8, because if I cut away 8, I've got nothing left in the width. So that's not going to help me. And so this is the only answer that's within those bounds. All right, now let's evaluate that critical point. This is our critical point. Critical point. And now let's evaluate it. Now again, because we have a nice polynomial, let's just take the second derivative and do the second derivative test to test for concavity to determine whether this critical point is a local maximum or a minimum. So if we take the second derivative, I'm just going to go back up to the polynomial form of the first derivative, and I will get 24x minus 144, which tells me if I evaluate the second derivative at 2.945, I get a negative 73.32. So it's concave down, right? Concave down looks like that. So that's telling me the point 2.945 has to be a local maximum. Local maximum at x equals 2.945. All right, now let's evaluate the and find the global maximum. So we have a couple endpoints, but f of 0, it's not f of 0, it's v, right? We're going to evaluate the volume. So it's v at 0. Of course, we cut nothing away. You're not going to get any volume, so it makes sense that would be 0. F of 8, okay, now you're cutting everything away. But if I plug that back up into my volume function, I get 0. So that means that, again, I'm using f. I'm meant to use v, because v is the function. So v at the volume when our cutaway piece is 2.945, that gives me a volume of 420.11 square inches. Okay, so our conclusion is that the maximum volume is 420.11 square inches when the squares cut from the corners. I'll just abbreviate. When the squares are 2.945 by 2.945 inches, because all our units are in inches. All right, so that's our conclusion. Okay. All right, I got one more example before I go on to the, before we get to the practice problems. Now, the practice problems that I put in this section are, they're good practice as kind of a warm-up for the homework, but the homework is a little harder. So that's why I'm going through some harder problems. Now, the practice problems are easier than these examples that I'm doing right now. So hopefully between the practice problems and then these examples, you'll have good luck with the homework. So, okay, I'm just going to go. This is definitely the hardest problem, and it's harder than the homework. So you can stop the video right here if you want to, if you don't want to see this one. But I like this one because it's a good example of how trigonometry, how we can use the trig functions. Okay, it's a good example of using trig functions in a real world problem. So in this problem, we have a rain gutter. It's constructed from a flat piece of metal, and the metal's then bent up at some angle and is bent into thirds. So each section is 10 centimeters, 10 centimeters, and then the flat bottom is 10 centimeters. Okay, and then we're bending it up at some angle. And we want to find the value of the angle, theta, that allows the rain gutter to carry the maximum amount of water. Okay. So you can imagine at a shallow angle, it's not going to carry much water. But if you bend it up too high, it's not going to, it's going to restrict the volume as well. So, now I am going to say that when I think about this problem and I want to put bounds on it, I'm going to say our angle has to be between 0 and pi over 2. Right, because 0, obviously, you're going to get no volume. At pi over 2, you can imagine that, it's just going to make this thing narrower. So, like, pi over 2 would be an angle of 90 degrees here. And so, you can imagine that if you have too steep an angle, you're just going to be pinching it off. So, let's make that assumption. And, I'm also going to make the assumption that the volume, because, we don't really know how long this gutter is, right? All we've got here is a cross-section, but I'm going to assume that the volume will be maximized when the cross-section is maximized. When the cross-sectional area, cross-sectional area is maximized. Okay. So you can see we've got this trapezoid, right? It looks like a trapezoid. And the area of a trapezoid, this might be something that you have to look up because it may be something that you might not remember, but you take the average of the two bases, which are the parallel sides. Okay, we're going to call it B1 and B2. We add them together and then divide by 2. So basically averaging them and then times the height. So that's the area of a trapezoid. Now I'm going to draw in the height here, and I'm going to draw it down here to this corner. So here's the height. Okay, this length here is B2, I'll call it B2. And this length here is B1. Okay, those are our two bases, the two parallel sides. Okay, so we need to find expressions for the bases and the height in terms of an angle. And you can see already here, I've got a nice right triangle. Okay, so if I notice I'm bending this thing up at an angle, this angle here, and because I drew some parallel lines here, you can see that because these are alternate interior angles between two parallel lines and a transversal, then if we bend it up at an angle of theta, then this other angle is theta as well. So, okay, so you can see this right triangle. And I am actually, let me draw another height over here, just so you can see this a little better. So this is also h. And this distance here is b1, right? This distance between the two heights that I drew is b1. And I'm going to call this x and this x. Okay. And so I'm gonna find actually, okay, so what I can do is I can say that the sine of theta, is opposite over hypotenuse, right? So that's h, opposite is h over 10. So that tells me that h is equal to 10 sine of theta. Okay, so now I have h in terms of theta. I can also take, the cosine of theta is adjacent over hypotenuse. So that tells me that x, this little leg here, is 10 cosine of theta. Okay, so now I can find that my my b1, that's just given, that's just 10, right? And b2 is just going to be b1 plus 2 of these x values on either side, right? And then I have an expression for h, so, for h. But I can express b2 as then 10, because that's b1, plus 20 cosine of theta. Okay, so now I'm going to use I have an expression for b1, have an expression for b2, right, in terms of theta, and I've got an expression for h in terms of theta. So I've got everything I need to plug into my expression for area. Okay, so that's going to tell me that, let's put a little, all right, so I'm going to get that the area is equal to 1/2, and then I'm going to add the two bases, so 10 plus 20 cosine theta, and then times the height, which is 10 sine theta. Okay, so there's an expression for area, the cross-sectional area. And actually, I'm going to make this a little higher because make sure I have plenty of room here. All right, so that I can just simplify as 1/2 20 plus 20 cosine theta times 10 sine theta, right? Just combine those two 10s. Now, I'm going to bring the 1/2 inside here, so I'll get 10 plus 10 cosine theta times 10 sine theta. All right, I'm going to factor out a 10. I also have a 10 here, so that makes it 100 times 1 plus cosine theta times sine theta. Okay, that's a little simpler. And now, because I have to take the derivative of this thing, right? So I don't want it to be, I don't want the function to be too ugly. It's going to get ugly, though. Not too ugly. I've seen worse. So, all right, I'm going to come over here. Let's take the derivative of this thing. A prime. I call it A prime. Now this 100 just is it's just a constant multiplier. So I'm just going to bring it and just leave it on the outside. And then I'm going to use the product rule. Actually, I'll put brackets here because I need to use the product rule on this part. Okay, so I'm going to take the derivative of the first. Let's see. Yeah, I can take the derivative of the first. Okay, so the derivative of 1 plus cosine is going to be minus sine of theta times the second, which is sine of theta, plus the first, 1 plus cosine theta, times the derivative of the second, which is cosine theta. Okay. All right, so now let's clean this up a little bit. So I get 100, and this is minus sine squared theta, and then I get plus cosine theta plus cosine squared theta, right? Just distributing that cosine. Alrighty, now I've got a minus sine squared and a plus cosine squared. So it's not the Pythagorean identity. It is a double angle, but a double angle is not going to help me here. Probably the best thing here, because I've got cosine and cosine squared, I'm going to replace this sine squared with 1 minus cosine squared. Right, so I'm going to replace this with 1 minus cosine squared theta. So I'm using the Pythagorean identity. Sine squared plus cosine squared equals 1, subtracting cosine from both sides. So I get an expression for sine squared in terms of cosine. So now I've got everything in terms of cosine. Cosine theta plus cosine squared theta. Okay, see, I told you it's kind of ugly. So, but like I said, this is probably harder than any of the homework problems. The homework problems are harder than the practice problems, but they aren't quite as hard as this. All right, let's clean this up here. Okay, so what do we got here? Now I'm going to take this cosine squared and this cosine squared and combine them. I'm going to distribute this -1, so I get 2 cosine squared theta when I combine these two cosine squareds. And then I have a plus cosine of theta, and then I'm going to have a -1. Okay, so now you can see it looks like a quadratic equation, right? So what I'm going to do, just to make it a little easier, I'm going to say let r equal cosine theta, so that you can see it looks more like a quadratic. So then I'm going to get 100 times 2r squared plus r minus 1. Now this one factors nicely. So let's factor by, I like to split the middle term. So I'm going to make it 2r minus r minus 1. Oops. Should keep my brackets consistent. I've been using a square bracket. Okay, so all I did is I look at the 2 times -1. I'm looking for factors of -2 that add to 1. So factors would be 2 and -1 add up to the positive 1r. All right, so let's keep going. So now I get 2r, that's r plus 1, and I can factor a -1 out of the last 2 terms, and I get r plus 1. Oops. And so I get 100, and I'll have r plus 1 times 2r minus 1. All right. Now, so we factored it in terms of r, and now this is the derivative still, right? and now to find the critical points, I've got to set it equal to 0. Okay, so I'm going to set this equal to 0, which gives me r is equal to -1, or r is equal to 1/2. Now remember, r is cosine theta, so cosine theta equals -1, or cosine theta equals 1/2. Okay. Now, if you remember our restriction, I said that basically theta is between 0 and 2 pi. So basically the first quadrant. And so in the first quadrant, cosine of theta can never be -1. So this one has no solution. No solution in the first quadrant. So 0 less than equal to theta less than equal to pi over 2. Okay, but we do have a solution for this one, right? Theta then is equal to pi over 3. Cosine of pi over 3 is 1/2. So, so that's telling us we have a critical point at pi over 3. We're getting close now. Critical point. Okay. We have a critical point at pi over 3. Now we just have to prove that that's a maximum, because we're trying to find the maximum. All right, so what do you think? We should take the second derivative of this thing. Let's just do it. All right, so I'm going to go back up here and take the derivative of that before I factored it. And okay, so this 100 stays out here. All right, and then when I take the derivative of cosine squared, I'm going to use the chain rule. So it's like the outside function is the square, and the inside function is the cosine. So I'm going to get 4 cosine of theta, and then the derivative of the inside function is a minus sine of theta. Okay. And that was the hard part. The next part, to take the derivative of cosine is a minus sine. Right? So there's going to be minus sine of theta. And then the derivative of minus 1 is 0. Okay, so there's our second derivative. And because you know, we're dealing with angles in the first quadrant, okay, where both sine and cosine are always positive, you can see these negative signs are going to make it so that this is always negative. This is always negative in our interval that we're interested in, which is between 0 and 2 pi, or sorry, pi over 2. Right? Always negative. So concave down, right? Which tells us that we have a local maximum at theta equals pi over 3, which is 60 degrees. Okay. So our conclusion is, I'm going to come back up to this white space here, that the rain gutter carries the maximum water, when theta equals pi over 3, which is 60 degrees. So that's kind of cool, right? Really a practical problem there. All right, well, that's all I have for you today. There's some good practice problems here. They are not nearly as hard as these examples that I've been giving you, so hopefully they'll seem easy. The hardest part of all of these is just setting it up and figuring out what your function is. So try the practice problems, and then there is an exit ticket, and then you'll be done for the day. Then you can start on the homework. So, all right, we'll see you later.